The next step in electrochemistry is to connect cell potentials to spontaneity from the thermodynamics chapter and to the equilibrium constant. To do this, we need to dive into a few definitions and introduce a new helpful constant. Okay, so let's take a look at volts. We've been using these for cell potentials. Volts are made out of joules per coulomb of charge. So you can think of that as the amount of energy and the electric charge. Now, back when we were studying thermodynamics, we realized that energy is measured in joules or kilojoules. So what we really need to do is isolate our joules from our volts equation. When we do that, we end up with joules is equal to volts times coulombs. We also know from our cell potential lessons that volts are always reported in a ratio. It has a lot to do with the types of chemicals that are used. In our redox equations, there's different amounts of electrons transferred in each different reaction. We need to make sure that we account for those different amount of electron changes. So what we're going to do is we're going to introduce a new idea, and we're going to replace the coulomb part of this equation and instead figure out exactly how much charge is transferred, because the different amounts of electrons will be different. So we need a new constant. Our new constant is really just a ratio of how much coulombs each mole of electrons will transfer. If you think about it, one electron has a charge of 1.602 times 10 to the negative 19 coulombs. And that is for one electron. And if we multiply that times a mole of electrons so that we can use stoichiometry, we have times 6.022 times 10 to the 23 electrons inside of 1 mole of electrons. And that number gives us something called the Faraday constant. You can think of it as 96,485. I know, super easy to remember. The units on that are coulombs per mole electron. This unit is extremely helpful for changing our volts into energy units. Okay, now we're ready for a few equations. If we multiply together our number of electrons, or rather our mole of electrons, times the Faraday constant, times the voltage in the cell, or you can call it the cell potential, that gets us units that look like mole of electrons times the coulombs per mole of electrons times the joules of energy per coulomb. This makes it so that our units all cancel out nice and neat, so that we'd end up with energy units. One more thing that we need to add onto this equation before it's good to go is the negative sign. If energy is leaving our system, we need to define it as being negative. Now, this kind of energy has the ability to do stuff, just like the energy that's released when a reaction releases gas, and that gas can push a piston up in a container. This energy is now available to do electrical work, like light up light bulbs or turn on an electrical device. So we can define this as equal to work. Now, if you remember from your electrochemistry chapter, we used to define work as equal to our Gibbs free energy. That helped us define whether something was spontaneous, which you can think of as spontaneously available to do work. So now we have this new equation where we relate an electrochemical cell ability to do work. You can see in this equation that there's a lot of useful information about predicting spontaneity. Delta G is spontaneous when it's negative. There's a negative in front of this equation. So that means that our cell potential can actually be used to predict spontaneity. If your E cell is positive, the reaction is spontaneous in that direction. We also need to remember how the Gibbs free energy relates to equilibrium. In that equation, the standard Gibbs free energy is equal to negative gas constant times the temperature in Kelvin, natural log of the equilibrium constant. If we use a little substitution, we can see that our expression for electrical work, the moles of the electrons times the Faraday constant times the cell potential, is equal to the expression that we used with the equilibrium constant. Now we can do a little bit of dividing and get a new expression for our cell potential. We'll see that our negatives cancel. That always makes me happy. And that this is going to be equal to the gas constant times the temperature divided by the moles of electrons transferred times the Faraday constant times the natural log of the equilibrium constant. Under standard conditions in thermochem problems or in electrochem problems, you're going to have 1 atm of pressure and 298 Kelvin, which is really fun because in gas law problems, standard conditions are considered 273 Kelvin, but for thermo problems, we keep it at 25 degrees Celsius or 298 Kelvin. In those cases, you can use a shortcut equation where the electrical cell potential is equal to 0.0257 divided by the number of moles of electrons transferred times the natural log of the equilibrium constant. I personally like to remember this first one just in case the temperatures are weird. And that's pretty much all that you need to know to be able to conquer problems that involve a crossover between electrochemistry, thermodynamics, and equilibrium.